Hello and welcome to the SpaceX Transporter-3 rocket launch, which is scheduled for liftoff in about half an hour's time. My name is Michael and I'm going to be your host for this live stream. I'm pleased to say I'm joined by a whole host of guests as well. One of those is Rolanda, a systems engineer from Nano Avionics, who's going to be my technical sidekick for the first part of this live stream. We're also joined online by various stakeholders on the satellite mission. So say hi everyone who's joining us online. Thank you to all the guests who've joined us, and thank you for joining Nano Avionics for this event, where as a small satellite manufacturer and mission integrator, we have 3 satellites that we've developed and built for our customers on board this SpaceX rocket. One of these satellites marks the start of SEN's mission to create an ETV satellite constellation. This constellation will democratize space using video to inform, educate, inspire, and benefit all humanity. The 16U satellite that's launching today, named ETV-A1, will stream real-time videos from space, making the views of our planet universally accessible to billions of people, and gathering news and information that's useful to inform decisions and address rapidly evolving disasters and crises. The second satellite that's on board the Falcon 9 today is the DEWA-SAT-1. This is named after the Dubai Electrical and Water Authority. This 3U satellite with an Internet of Things or IoT gateway will use satellite network connectivity and signals from IoT terminals on the ground to enhance DEWA's flexibility and agility in monitoring and managing Dubai's electrical and water networks. This includes the largest single-site solar park in the world. This is the first of 2 satellites that Nano Avionics is scheduled to launch for DEWA this year. When we have the Q&A after the launch goes into its coast phase, we might touch on its largest sibling. Finally, the third satellite that will be launched today carries hyperspectral images that have been designed by a student team at Norwegian University of Science and Technology. This satellite is named HIPSO-1, and it will be one part of NTNU's ambitious multi-agent marine observation system. This system is designed to study algal blooms and other biological activity in the oceans. NTNU will combine observations from the orbiting satellite with those made by autonomous vehicles above, on, and beneath the ocean surface. The data from HIPSO's onboard optical imaging payloads will support environmental monitoring and management of marine resources and contribute to our understanding of climate change's effects on Earth's oceans. So that's a quick introduction of the 3 satellites that are on board the Falcon 9 today. Now I want to briefly go through the schedule for the rest of today's live broadcast. So in the next 15 minutes, Rolanda is going to talk us through a little bit more about the types of satellites that are on board today. Then we're going to transfer over to SpaceX for their live stream of the countdown and liftoff. Once the Falcon 9 has reached orbit and is in its coasting phase, we'll have roughly 40 minutes during which we'll have a Q&A with some of the customers and stakeholders involved in the different satellite missions that are launching today. Finally, we'll return back to SpaceX to hopefully see a successful deployment of those satellites, which is what we're all waiting for. So that's the plan for today's live broadcast. Now it's time to talk with Rolanda to find out a bit more about some of the technical details of these satellites and the Transporter-3 mission that they're going to be on. So great to have you with us, Rolanda.
Thank you. Great to be here.
And can you tell us, is there anything special about this particular mission that's launching today?
Yeah, so it is a very exciting mission for us because it is the first time that we have even 3 satellites on the launch vehicle, because before that we had up to 2 satellites. So one more interesting thing about this mission, that we are launching a 16U satellite, which is the heaviest satellite made by Nano Avionics so far. It weighs around 29 kilograms. And also only few satellite manufacturers in the world have ever launched 16-unit satellites into space. So we are very excited to gain this flight heritage now.
Fantastic. Yeah, it's a really big day for Nano Avionics. And you talked about the 16U satellite. Maybe you can talk us through a little bit more about the 3 satellites in terms of their makeup and maybe some of the differences between them and how they'll operate.
Yeah, so the satellites are all different size. So we have a 3-unit satellite, 6-unit satellite, and a 16-unit satellite, which we see in the slides. So to understand better, 1 unit of a satellite is basically a 10 centimeter cube. So 3-unit satellite could be compared to a milk carton. 6-unit satellite can be compared to a shoebox, and a 16-unit satellite is something like a microwave oven. Though all the satellites are of different size, but all of them have very similar and flight-proven nano-avionics subsystems. For the subsystems, we need power, and power is generated using solar panels. As we see in the slide, DEWA-SAT 1 and ETV-A1 both have a single deployable solar panel configuration, and HIPSO-1 has a stowed solar panel configuration, which means that solar panels are attached to the satellite walls. Having power, having subsystems would not mean anything if we couldn't communicate with the satellite. So all of these satellites have redundant communication system using S-band transceiver as a primary transceiver and the primary communication, and UHF subsystem as a secondary communication. These transceivers have antennas, so S-band antennas are attached to the satellite walls because these are patch antennas, and UHF antennas are in a form of splitter, and a splitter has 4 monopole UHF antennas which are deployable and could be seen on the 3-unit mockup that we have on the table. And ETV-A1 will also have an X-band transmitter, which is needed for a big amount of data transfer because, as Michael already mentioned, it is an imaging mission, and they will generate a very big amount of videos of the Earth. Also, a crucial subsystem to successful mission is an ADCS system, which is for attitude control and determination system. All these 3 satellites have quite different configuration of ADCS system. So talking about attitude determination, DEWA-SAT 1 has a set of sensors which include sun sensors, magnetometers, and gyroscopes. HIPSO-1 and ETV-A1 being optical missions, they have quite bigger requirements for pointing accuracy. So HIPSO-1 also includes an IMU and 1 star tracker, and ETV-A1 has a very similar configuration, only it has 2 star trackers on board. So we have talked about the attitude determination. Mm-hmm. And for attitude control, every satellite has a set of reaction wheels and magnetorquers.
So, as the saying goes, 3 is the magic number. So hopefully 3 satellites today is going to be the magic number as well, although we hope for many more as well. Rolanda, maybe you can tell us a little bit about the rocket that's going to get them up there into space and some of the orbital parameters of these missions.
Yeah, sure. So this is Transporter-3 mission. It's quite obvious there were 2 rideshare missions before. So we have already flown our satellites on first 2 missions. So on the first we had 1 satellite, and on Transporter-2 we had 2 satellites. Now we have 3. So this launch vehicle will bring our satellites into 520 kilometers orbital altitude. The satellites will be released into sun-synchronous orbit, which has an inclination of around 97.4 degrees. The satellites will be flying around 7.5 kilometers per second, and the orbital period will be around 1 hour and a half.
Mm-hmm. And what about the lifespans of these different satellites once they're up in orbit?
Yeah, so HIPSO-1 and DEWA-SAT-1 have a very similar lifetime in orbit, so it's around 5 years. They do not have propulsion, so they will deorbit naturally. When their mission is over, ETV-A1 would fly naturally for 13 to 14 years. However, it has propulsion on board, so the lifetime might be increased if needed. But when the mission is completed, it will also deorbit naturally.
Okay. Well, fascinating to hear how that whole process is going to work once they're up, but now comes the critical moment of getting them up into space, and we're ready to transfer over to SpaceX's live stream to see the countdown, launch, and successful liftoff, we hope, of that Transporter-3 mission. Once the Falcon 9 hopefully reaches orbit, we'll come back to our live stream while it's in its 40-minute coasting phase, and we'll have a quick Q&A and meet some of the guests who are going to join us remotely. But for now, it's time to go over to SpaceX and watch that live stream of hopefully a successful rocket launch for Falcon 9.
Startup, which means that the rocket's own internal computers are now autonomously controlling the launch countdown. As I mentioned before, our satellites they're inside the fairing. They continue to be healthy. The team is tracking no issues on the rocket. And as a reminder, if we don't launch today, we do have a backup opportunity tomorrow at the same time. And we have just 2 minutes to go before launch. At this point in time, LOX load on the second stage has just completed. And we can see the white gaseous clouds around the vehicle as, like I said, LOX load is complete on second stage as well as first stage. So those lines will be venting from the TE.
Ground gas closeouts.
The next milestone we're coming up to is startup. You'll hear the call out for that at T-1 minute. And that's the indication that the flight computer has taken over.
Falcon 9 is in startup.
All right, there's that call out. Falcon 9 is in startup. At this point in time, stage 1 and stage 2 are beginning to pressurize for launch.
LD, go for launch.
And there was our final go for launch today from our launch director. At this point in time, as we approach T-minus 30 seconds, all systems are go for launch.
T-minus 30 seconds.
Let's listen in to the final countdown.
T-minus 15 seconds. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Ignition and liftoff.
Vehicle's pitching downrange.
Gear pressures are nominal. Power and telemetry nominal.
All right, as you can see, Falcon 9 has cleared the tower, lifted off from Cape Canaveral Space Force Station. We just heard the call out that the vehicle is supersonic. We're currently going to throttle down the engines in preparation for max Q coming up.
Max Q.
Oh, there we heard it. So that was the moment of greatest aerodynamic pressure that the vehicle will experience in flight today. Everything looking nominal with stage 1 trajectory. Now we have 5 events coming up in quick succession. MECO, or main engine cutoff, stage separation, stage 1 flip, second engine start 1, and the boost back burn. And you can follow along with those events there on the timeline at the bottom of your screen. Beautiful view of the Florida coastline. Main engine cutoff coming up in just under 30 seconds. As I mentioned before, we will be attempting to land the booster back on land at landing zone 1. This is known as return to launch site, as opposed to a drone ship landing.
MECO. Stage separation confirmed. startup.
Stage 1, boost back startup.
So you can see there on the right-hand side of your screen, second stage MVAC engine has ignited. The first stage on the left-hand side is performing the boost back, which, as you saw just moments ago, the first stage flipped itself over and is now making its way back to the coast of Florida. Everything looking nominal with second stage trajectory there on the right-hand side of your screen.
Stage 1, boost back shutdown.
All right, so there we heard the call out that the boost back burn has concluded. That was the first of 3 burns that the first stage will perform today. And we can see the grid fins beginning to deploy there on the left-hand side of your screen. The next event we have coming up is fairing deployment. All right, there you can see the 2 fairing halves have separated, fallen away from the vehicle, exposing the 105 spacecraft to the vacuum of space. As a reminder, we will be attempting to recover these brand new fairing halves once they make their way back to Earth. We're currently in the first of 2 MVAC burns. This first one will last until T plus 8 minutes and 26 seconds, about another 4 minutes from now. Beautiful views from the first stage there on the left-hand side of your screen and the second stage on the right. The next milestone will be the first stage booster re-entry burn. Falcon 9 executes an entry burn to slow itself down before hitting the dense part of the atmosphere. Without this burn, relying on the atmosphere alone to slow down the Falcon 9 would put unnecessary strain on the rocket. And there we can see the east coast of Florida.
Stage 2 on a nominal trajectory.
Space Coast there in the background of on the left-hand side. Once again, we are launching the Transporter-3 mission today. This is SpaceX's 3rd dedicated smallsat rideshare program mission, and it's our 2nd mission of 2022. SpaceX is targeting at least 3 dedicated rideshare flights to sun-synchronous orbit per year, and we also offer opportunities for a ride to orbit on our Starlink missions, which launch every couple of weeks. Smallsats can ride to space on SpaceX's Falcon 9, Falcon Heavy, as well as Starship in the not-too-distant future. On the left-hand side of your screen, we can see those grid fins have deployed. Falcon 9 has 4 hypersonic grid fins positioned at the base of the inner stage, and they orient the rocket during reentry by moving the center of pressure. We can also see some white puffs of gas coming off from Falcon 9. Those are cold nitrogen gas, which help with attitude control. After first stage landing, the second stage will cut off its MVAC engine and relight it approximately 45 minutes later for deployment of all 105 spacecraft. As for first stage, its next event is the entry burn.
Stage 2 FTS has safed.
Stage 1 entry burn startup.
And there on your screen, we can see that that entry burn has begun. Once again, this burn is designed to slow the booster down as it returns through the dense part of the atmosphere.
Stage 2 on nominal trajectory.
As we just heard there,
Stage 1 entry burn shutdown.
Everything continuing to look good with second stage. As I mentioned earlier, we'll be attempting to recover this booster for the 10th time today, and we're targeting a land landing at landing zone 1. The first stage has just one more burn left, the
Stage
landing
1
burn.
FTS is safe.
It begins just before touchdown and provides the booster a soft descent before landing. About the same time that Falcon lands, we are expecting SECO, or second engine cutoff, one of our second stage. Just a few seconds away from landing.
Stage 1 is transonic.
Vehicles traveling around 900 miles per hour. Really puts the deceleration into perspective. In the span of less than a minute, we'll have reduced from twice the speed of a jet
Stage 1 landing burn.
all the way down to 0 as the rocket lands. There's a view on the right-hand side.
Stage 2 in terminal guidance.
Of the landing, back at landing zone 1.
Stage 1 landing like before. Stage 1 landing is confirmed.
As you heard from the call out there and from the cheers behind me, we have successfully landed this Falcon 9 for the 10th time. It's also the 102nd recovery of an orbital class rocket.
Nominal parking orbit.
All right, so we just heard their second stage.
Welcome back to the Nano Avionics live stream of the Transporter-3 SpaceX mission on the Falcon 9 rocket. As we've just seen, that rocket is now in its coasting phase, which means we have about 40 minutes to have a discussion and learn a little bit more about the satellite missions that are up on board that. To kick us off, we're going to talk a little bit about Nano Avionics and what we do here. To give you a brief introduction, Nano Avionics supports companies during different stages of their development and tailors the best solutions for them. These can range from a shared satellite service where multiple clients can share mission costs, through to dedicated satellite missions and end-to-end service provision, which is the case for the 3 satellites that are flying today. Right now, I have the pleasure of being joined by Šarūnas Kazlauskas. Šarūnas is content manager here at Nano Avionics, and he's going to tell us a little bit more about the work we do here. So before we go into the details of each of these missions, and all of the nerdy technology, can you just kick us off by telling us a little bit about small satellites, right from the basics? What are they? How did they come about?
Sure. So small satellites have been here since the very early days of space. Obviously, you could call the very first satellites ever launched small satellites. But I guess the more important distinction comes now in the new space days, where we have seen the CubeSat standard being sort of standardized, and a lot of commercial applications being developed on that standardized modular platform. So, and CubeSats originated maybe 20 or so years ago as a university project to kick off aerospace engineers and give them better experience with developing space hardware and getting data and doing research in orbit. And then later on, it's been adapted by a lot of commercial satellite suppliers to basically take advantage of all the electronics that have been reducing in size thanks to smartphones and all the other technology that was now very affordable and small, and you could fit a lot of interesting technologies in a small package, like one of these satellites that are just as big of a shoebox or even smaller, and do a lot of interesting things with them in orbit.
Fantastic. So you talked about those interesting things that can be done, but tell us a bit about which are the most common applications and also some more of the advantages of this miniaturization of satellites that you've been discussing.
Sure. So some of the advantages are obviously small size. You don't need to build a satellite that is a size of a school bus and pay for a whole rocket to launch it into space. You can have something really small and you can reduce the launch costs for it. One of the use cases for these small satellites, you could have an optical imager, you could detect temperatures here on Earth all around the globe, you could look at some of the radio frequency emissions if you're a company that is interested in expanding its network capability for mobile services and so on. And of course, you have the growing market of IoT, Internet of Things. So you could have devices on ground sending signals and data about various various assets on ground, farmland, offshore, wind farms. The logistics companies could also benefit from a lot of their asset tracking with these technologies. So those are some of the main areas that small satellites have been aiding in. Of course, you can also do a lot of fundamental research with them.
Yeah, and some of those use cases that you've mentioned, Earth observation, IoT, we're definitely going to get more into those as we learn more about the specific satellites that we're discussing today. We've talked about this category of like CubeSats, small sats, and I assume most people would think, okay, this is a pretty like generic category, but actually it's quite diversified. So could you give us a bit of an overview of what falls under this umbrella of like small satellites, and then what the range is that we're talking about? Because even in today's mission, we've got quite a distinct range between the smallest up to the largest satellites.
Yeah, exactly. You can have very, very tiny satellites that weigh just a fraction of a kilogram and can fit in the size of in your palm, up to satellites that weigh around 500 kilograms. That would be called, that would still fall under the umbrella of small satellites. So it's a very big range, and you have a lot of sort of diversity in that area. And for what we do at Nano Avionics, we mostly work with nano and micro satellites at the moment. So we started off basically with a 3-unit satellite like you can see here, and sort of went step by step from there. We standardized our 6-unit platform, and then we even saw more interest from the market for larger satellites to have bigger payloads, have more capability, more onboard power on the satellite. So then we went to 12, 16 units. Some of the satellites flying today that we'll see are actually pushing the limits of this nano satellite, of these nano satellite platforms. So the 16U satellite by SEN is, for example, probably one of the heaviest satellites we have launched yet. And it's really pushing the limits of that system on pretty much every front. So because of that, we also saw a demand for even bigger satellites. And last year we introduced our modular microsatellite bus, which can now weigh even up to over 100 kilograms with the payload integrated to it. And yeah, we're actually in the process of already doing the first environmental test for our first MP42 satellite, and hopefully we'll see it launch in just a few months as well now.
Yeah, fantastic, and really interesting to see how it's expanding, how the scale is increasing, and also the capabilities as well. One capability we should focus on a little bit is Earth observation, which you've already mentioned as like a critical use case for small satellites. 2 out of the 3 satellites that are launching today have imaging payloads on them. Is this something new for Nano Avionics? And talk us through any of the specific requirements from a manufacturer's point of view once you have these imaging payloads on board.
Yeah, so we'll definitely, we'll hear more about the Earth observation satellites flying today, and they're not the first ones that we've been working on. So Nano Avionics has been working with multiple imagers from various suppliers around the globe, as well as supporting our customers with their own developed optical imagers. So I think we've worked with over 10 missions like that so far. And some of the technical challenges are, of course, once our clients are trying to push the limits of imaging from space, going with ever higher resolution and more magnification, there comes a lot of issues with getting very precise targeting with these satellites. So if you have a very large telescope inside of the satellite, essentially, you need to make sure that your pointing accuracy to the area that your client wants to observe is is pretty much perfect. There's also a lot of moving mechanical parts in the satellite that might cause unwanted vibrations. And if you have a very, again, long focal length, it can introduce jitter and other disturbances in your video or photo footage. So we've dealt with that at Nano Avionics on our subsystem level and our structural frames for the satellites. A lot of the optical images can have a lot of heavy weight glass inside them. So then you need to develop frames that are sturdy but still light enough to actually accommodate those payloads. And then of course they generate a lot of data by taking a lot of pictures or video of Earth, and so you need also payload computers, payload controllers that can actually manage the amount of data that is going through that system, and then of course reliably transmit it down to Earth at also fairly fast data rates. So there's going to be a couple of missions on this launch that are hopefully going to benefit from all these developments that we've been working on for years now.
Yeah, and it's fascinating to see that development of as the technologies get more complex, or the quality of the imaging and the demands. So from the manufacturer's side, the demands increase as well, and you have to keep problem solving and finding solutions. Thanks so much, Shorunas, for sharing your thoughts and sharing that point of view with us today. It's time now to jump into a breakdown session of each of the satellites that are going to be going up on the Transporter-3 today. And first of all, we'd like to start with the company SEN. We're joined now again by the founder and CEO, Charles Black, who's going to talk us through a bit about the payloads, the services, and the bigger picture of what SEN does. So, first of all, the ETV-A1 is a rather large satellite, a bit too big to fit on our table here. And with that large size comes probably some big ambitions. So, Charles, could you talk us through a little bit about the overview of SEN and your goals as a company?
Yeah, sure. So the vision of SEN really is to democratize space using video to inform, educate, inspire, and benefit humanity. It sounds like an ambitious vision, and obviously there's a number of companies that take images of Earth and known as the Earth observation market. These are satellites that will take pictures of Earth, and there are satellites already in existence and constellations that take still pictures, and some that take radar imagery or near infrared. And those images are then analyzed back on the ground and provide really valuable, useful information about the health of the planet. What SEN is doing is actually introducing a new type of data into the Earth observation market, which is video, including real-time and near real-time video. And although we are still going to channel our imagery through an analytics layer through partners who develop analytics to provide useful insights, the really interesting thing about video as a type of data is that it has storytelling power, and the human brain can interpret and extract information from just watching a video without an analytics layer. And so that opens up a whole new business model, we believe, for Earth observation for our type of data, which is a direct-to-user model, whereby we're actually going to capture video, both real-time and recorded video, and provide that directly to users through an app, which will be accessible on smartphones and through web browsers, and enable people to witness essentially major goings-on the planet. And this comes back to the idea of democratizing space. So the traditional Earth observation model is very much about capturing forms of data, analyzing them and supplying those to businesses and governments. And we want to actually empower people to witness the evolution of life on Earth and eventually beyond, because SEN is planning to eventually put cameras around the moon and Mars. But we're focusing on Earth to start with, because that's where 7 billion people live, and there's a lot going on, and we want to just really monitor the health of the planet with a real focus on environmental events that impact hundreds of millions of people every year, and just empower people by giving them this information directly. And we hope that will not only enable people to take action, but also inspire really global change about the way in which we look after the planet. So SEN's vision is democratizing space using video, and it's all about informing and educating and inspiring people to try and benefit people on the planet.
Brilliant. A really inspiring vision and a really important one at this time as well. You've explained a bit about how you're adding something unique to the Earth observation sector. Could you tell us more specifically about Earth TV now? What do you hope for in terms of how it will enable individuals and organisations to use orbital perspective?
Yeah, so one of the things about ETV is that it has several cameras on board with different spatial resolutions, ranging from sort of a wide angle view, which is almost looking like a 1,000-kilometre scene, down to a very high resolution imager that can see down to about 1.5 meters of the ground per pixel. And the idea of having multiple cameras is all about putting life on the planet into perspective, because I think the human brain understands context. So if you look at the things we want to film, for example, environmental events, you need to be able to see that at different spatial resolutions. For example, flooding or a hurricane can often cover several hundred kilometers, so there's no point just looking at a very, very small scene. So we want to actually see the whole of, for example, a hurricane, and then be able to zoom down with the other cameras to actually then see human infrastructure on the ground, so that we can see, for example, the impact caused by a natural disaster. We can see roads and buildings and towns and bridges and railways. So you can actually then see what has been damaged, for example, by a natural disaster. So that's one thing about ETV. Obviously, it's all ultra high definition video, and it's capable of live streaming when we pass over ground stations to do that. The amount of live we're going to get will grow obviously with time. So although the system is capable of that, this is just the first satellite, and we're planning a constellation, and maybe up to 200 satellites in the next decade. And the amount of real-time video we'll get will increase dramatically per satellite as the constellation grows and as our operations grow and expand as well. So there has been some ultra high definition video from satellites before, but we believe this is the first satellite to do live ultra high definition video and to be capable of doing that. And it's taken several years of development to get to this point. So we're very excited. It's been fantastic over the last couple of years working with Nano Avionics as our satellite partner to help develop the satellite, and it's been a long journey. So the launch of this is a major milestone for us, but also it is just very much the first step, and we have a long way to go to fulfill our ambitions. But I think people familiar with engineering understand that it's always hardest to get the first one done, and then progress can go a lot quicker. And so we're obviously planning on working with Nano Avionics to build our next 4 satellites and to get those launched in 2023 to get us to a daily revisit from our highest resolution imager. And then after that, we want to scale dramatically with production line facilities for the satellite builds to get that constellation to where it needs to be to provide the level of information that we need for our business model of distributing vast amounts of data directly to users.
Fantastic. I mean, it's really exciting to be at that starting point, as you said, of what presumably up to now has been an iterative process and is going to iterate itself all the way to Mars and beyond. Talk us through some of the challenges that you've faced technically, and how you've been able to deal with them so far in terms of this small satellite, and also how the small satellite revolution might have helped you in that.
Yeah, absolutely. I mean, in terms of challenges, the idea goes back actually to 1990, when I first came up with the idea of we needed to send satellites into space to share with humanity this looking at Earth from space, because it gives you this different perspective of this borderless world and seeing the beauty of the planet, but also seeing how we need to look after the planet for the future of humanity. And so, of course, back then the challenge was that space was very much just for governments, and it was very expensive, and satellites were all the size of cars and buses. And so in terms of my challenges, I've had to wait a long time for the new space market to emerge, so that satellites have got smaller and smaller and lower mass, and therefore less costly to build, and of course less costly to launch. So the new space revolution has really been an enabler to do what we want to do, which is to enable us to build and launch a constellation of satellites, with reasonable costs, and with costs which enable us to obviously make a profit. So that's been essential. Also, even the emergence of the internet, because I came up with the idea before the internet had been invented. So we need that, because that then provides a global cloud platform for distributing the videos to users. And the first thing was, right, how do we want to be able to get really good quality video. So we really want ultra high definition video, and we want to be able to live stream as well. So that was the first technical challenge. And there wasn't any sort of off the shelf solution to do that in space. So I took the decision to actually develop that ourselves internally. And that whilst we wanted to partner with Nano Avionics for actual build of and launch and management of the satellites, we had to really create that payload ourselves. So as you mentioned, it's an iterative process, and we set about developing that, and actually had our first mission launched in 2019, where we developed some hosted cameras bolted onto a third-party satellite. And for us, obviously, in terms of the electronics and the software, it's very much the same system as being in its own satellite. Mm-hmm. So that launched in 2019 and successfully demonstrated. We had 6 4K video cameras, including steerable cameras, on a satellite built by Energia, the Russian spacecraft prime. So that proved, if you like, a very basic level of our technology. And what we've done is then iterate and develop and improve that to provide additional resilience, redundancy, and power. And that's what we've put as our payload into ETV. And then there's been a lot of challenges as well, just in terms of actually how you might be able to steer and the satellite. You don't want the satellite to have too much jitter or wobble, for example, when you're filming up to 30 frames a second of ultra high definition video. So it's been fantastic to work with Nano Avionics and their engineers, who have taken on all of these sort of challenges in terms of with the avionics and satellite build to accommodate our payload and optimize its performance. Hopefully this first satellite will really demonstrate this core technology and the unique business model that we're doing, and will enable us to get further support to go to the next stage of the business plan.
Yeah, plenty of challenges, as you mentioned, right from technical through to commercial. But ETV A1 is now on its way up, and hopefully is going to deploy pretty soon. Tell us a little bit about where you're going to focus its monitoring efforts. Then, obviously, now that you have your own satellite that you can navigate more. Where are you planning to monitor? And you've talked to us for a little bit, but maybe you could expand on your plans for the future to add to that monitoring.
Yeah, so we're going to monitor primarily environmental events. There are, on average, about 350 natural disasters actually a year, which impact a couple of 100 million people. And that's going to be the main focus. And of course, those take place all around the world. So you have wildfires, for example, at the moment in Colorado and in Australia and California. And then you have obviously other large-scale natural disasters impacting around the world. So that will be our sort of primary focus, is looking at those. But there are so many use cases for this data. One of the things that's going to sort of drive the exactly what the targets are for the initial filming will be engagement with potential customers. I mentioned obviously we're going to demonstrate from day one the direct-to-user model with the app and so forth, but we're also engaging with business customers such as insurance companies and NGOs that respond to natural disasters. And so we'll be working closely with our customers to define the filming targets in the early days. I think the second part of your question really was future plans. Well, obviously the ETV1, although it's not a tech demo in the sense of it's a fully functioning, very incredibly powerful satellite actually, with 4 ultra high definition video cameras and capable of live streaming. But of course, its limitation is being one satellite is its revisit rate over a particular point. So if, with the highest resolution imager, it's only every few days that we would actually orbit over the same point that we would wish to film. So that's why we need a constellation in low Earth orbit. So the plan is obviously then to go to the next stage of building 4 more, which will take us to a 5 satellite constellation by the end of 2023, which at least gives us daily revisit with the highest resolution imager. And obviously that's a more powerful capability. And then after that, of course, we want to improve revisit rate substantially by going to a large-scale constellation of satellites as quickly as we can.
Brilliant. Yeah, that makes perfect sense, and hopefully this is the start of that constellation that's gonna grow and expand over time. From up in space, maybe we can come back down to Earth and just think about from the user's perspective, how are they going to, you mentioned the app, so how are they going to be able to access this data, and how will they be able to interact with it as well?
Yes, absolutely. So CEN is a data business. Obviously, we have some really exciting technology that we need to deploy in space to enable us to capture this unique and proprietary data set. But the business model is twofold, really. Number one is addressing businesses and development partners who want to derive insights from the information. And there's such a wealth of use cases. Our strategy really ultimately is about creating a data library to allow third-party businesses anywhere around the world to access that data and analyze it. And we're really trying to build a sort of app store ecosystem model there, because we think it's inevitable in the future that a real-time or near real-time data set of what's happening on the planet has really far-reaching capabilities for third parties to analyze that data and provide insights to a wealth of end users. So that's the business side of things, is rather than us trying to do all of the analytics ourselves and address every single market, is to actually open it up to partners who actually sell into those markets, whether it's insurance or mapping, and to take our data and analyze it and use it there. In terms of the direct-to-user model, that will be accessed through an app. There's going to be a native app initially on Apple iOS and then on Android, but there's also a web version of the app which is accessible through a web browser on any internet-connected device, and that will look basically the same as the native app. And it'll enable you to watch videos, both recorded videos and live videos when we bring those online. And we're also going to offer augmented reality views. So there's going to be an option for the user to just click on a button, an AR button, and then we'll see an overlay of information, which initially will be geolocation information, but there's a huge amount of insights we can actually interpret and display to the user in real time around size, speed, direction, all of which we can extract from video. So the idea is to make the data as useful as possible directly to end users with both video and augmented reality views of Earth. And that will be freely accessible to people. The business model is based on creating mass usage for the data, and if we do that, then that creates a very sustainable, long-term, large business model. So that's how it will be accessible. So this is not the app's not available just yet, because we want to get the launch done, and obviously then there's the commissioning phase with Nano Avionics. So we'll get that done. So obviously we have a gap before we start then operating the payload and capturing videos, but the app will be launched ready for then in the spring.
Yeah, amazing. You can imagine the potential of the foundation Earth observation could have, as you said, for all these different uses. And I'm sure that many of our viewers will be off to download the app as soon as it's available and have a look at those incredible images that you're going to be streaming and showing back from space. Charles, thanks so much for joining us and sharing your really interesting insights on what's a really important day for you and your company as well. Perhaps you can stick around and give us your final comments once we see, hopefully, the successful deployment of your satellite in a few moments' time. But for now, thank you very much for joining us. And we'd like to turn on to the second satellite that's going to be deployed on our mission today, which is the DEWA-SAT-1. This satellite is being launched from the Dubai Electricity and Water Authority. Unfortunately, their representatives aren't available to talk with us today. So instead, we're joined in the studio by Harold Dubrikas. Hi, Harold. Thanks for joining us. You're a systems engineer here at Nano Avionics.
Yeah, hi Michael. Yeah, I'm Harold. I'm system engineer at Nano Avionics, and I was actually a system engineer of a DEWA-SAT project.
So obviously, Harold is also feeling exceptionally excited that that satellite is on his way up and will be deployed shortly. So let's find out a little bit more about the payload, the technology, and also the purpose behind this particular satellite mission. So maybe we can start with a bit of a general discussion about renewable energy, because as we'll find out, the DEWA-SAT-1 mission has a close connection with renewable energy. You know, we hear a lot about different emerging technologies that are important in this field, innovations in storage technology, decentralization models, artificial intelligence for managing complex energy distribution networks. What role can satellites play in this mix of green energy, and what are some of the ways that organizations might exploit the benefits of satellites for this purpose?
Yeah, that's a good question. So without going 100 years in the future, what we can do actually, how we can add value to the business today with satellite technology. So we can reduce the surveillance labor costs for large solar parks or wind energy parks. We can also apply the satellite data for forecasting, for expecting which regions are more favorable for solar power generation. And there are many more applications like monitoring, utilizing the IoT networks. So instead of having to constantly check your assets, you can just gather the data from all around the world, just using satellite technology and satellite networks.
Okay, it sounds very useful in general, and let's drill down a bit into the DEWA project in particular. So the first thing we should point out is that DEWA is not a space company. As we said, it's an electricity and water authority, and it's a ground-based business, but it does have a space division, and this division is aiming to improve its primary operations. So could you briefly talk to us a little bit about the problems that the DEWA-SAT-1 is aiming to address?
Yeah, well noted. So DEWA is actually, in simple words, we're just providing water and electricity to people living in Dubai residents. So we want to be on a cutting edge. We want to provide the most reliable service to their customer. And this is where we found a good opportunity to utilize the satellites. So their main goal is to improve the reliability of their network and to improve their forecasting capabilities. And here we can perfectly use the satellites to replace the labor-heavy ground surveillance operations with satellite technologies, with IoT network, which is being established for them. And therefore, by using these new technologies, we are not even improving the reliability of a network. We, at the same time, are also cutting costs for their operations.
Okay, so you get a double benefit of an improved network plus reduced costs.
Yeah, exactly.
Okay, sounds very good. And as you were mentioning, they're attempting to discover a solution to a problem that might be relevant for many large industries, monitoring and utilizing your large assets that you have. The 3U satellite, which is which the DEWA mission is using, that's being launched today, we're already working on a second satellite for DEWA. So what's the difference going to be between these two satellites that we're launching, and combined, what are their capabilities going to give for DEWA?
Yeah, that's correct. So besides the 3-unit satellite, similar to this one, we also right now developing a second satellite for DEWA operations, a 6-unit satellite, like in this form factor. And we actually two very different satellites. Mm-hmm. So the first one satellite which we are launching today is an IoT satellite, which is designed to gather the telemetry data from the various assets of DEWA electricity and water grid, and basically generating almost real-time data from their network. And meanwhile, the 6-unit satellite over here, it will be carrying on board a multispectral imagery payload. Mm-hmm. So this payload will be used for a Earth observation mission on the DEWA's area of interest. It's worth mentioning here that a good thing about multispectral data that the new use cases can be developed by basically improving the data processing even after the satellite deployment in space. So at the initial step of a mission, you may have certain applications which you'll use, but there is no one from stopping you from adding new use cases and getting more benefits in the future.
Amazing. So the technology can advance even once it's up in orbit and up in space.
Yeah, that's correct.
Fantastic. You were talking about Earth observation. So I guess one question, you know, we're in a pretty cold, cloudy region up here in Vilnius in Northern Europe. And obviously Dubai is a broadly kind of sunny, dry spot. What could you say about areas of the globe which are maybe less favorable for Earth observation or for these types of missions? How can satellite infrastructure be used in those cases, and what sort of technology should people be looking for in those regions?
Yeah, I will argue with you that if it's raining in your country, you cannot use Earth observation.
Okay.
Of course, there is some adjustments, but it's still completely adaptable to technology. But answering your question, so the Earth observation is not the only thing you can get from satellite. So it's very important to understand that there is an IoT networks, and the small satellites like we have here, they provide you capability to have your own small IoT network without being attached to any large-scale providers and basically operating everything on yourself and having your data centers, your own space capabilities. And these networks can be used for assets monitoring in the remote locations, in the deserts, oceans, for solar parks, wind energy parks. And it's very interesting that it might be even actually cheaper to establish own satellite-based IoT network rather than try to wire all your assets directly. So it might sound counterintuitive, but it can actually be cheaper to establish in that way.
Yeah, fantastic. That might well be, as you said, surprising, but it makes sense when you think about it. Yeah. Brilliant. Harold, thanks so much for sharing those insights about the payload, about the use case here, which is a really interesting one and maybe a little bit surprising in terms of some of the ways that a non-space organization could use satellite technology. For now, we'll say thank you very much, and we'll move on to talking to our third guests, who are from NTNU, the Norwegian University of Science and Technology. This is the HyPSO-1 satellite, and we're joined again by Roger Birkeland, researcher from the Department of Electronic Systems, and Sivert Bakken, a PhD candidate from the Department of Engineering Cybernetics at NTNU. Roger and Sivert, great to have you back with us. Thank you very much once again for joining us today. So, first of all, it would be great to hear a little bit more about the Earth observation capacities of this satellite. We've heard about ETV-A1 by SEN. There are a few fundamental differences between HyPSO-1 and that satellite. First of all, there's the size, but more importantly, there's the fact that it's using hyperspectral imagery. So it'd be great if you could, first of all, just talk us through how hyperspectral imagery is different and what are some of the benefits that it brings for Earth observation.
I can take this one. Hyperspectral imagery uses the electromagnetic spectrum in a different way than regular cameras, as it samples at a much finer detail. That means that we can go beyond just seeing red, green, and blue, as you do with regular cameras, and get more information about the different parts of the electromagnetic spectrum or different parts of colors that are observed from space. And with this extra information, we're able to say more about what we're looking at so that we can differentiate between this is green to something like this is healthy vegetation.
So it can tell you about not just different colors, but specific shades of colors. Is that type of thing?
Yeah, you could say that.
Okay, fantastic. And what might be some of the benefits of being able to do that in terms of Earth observation and your project?
For our project, this finer detail in the sample data would give us better information, and we can develop new algorithms that better exploit this extra detail in the captured images, so that we can say with hopefully higher accuracy what we're looking at.
Okay, fascinating. And as we started talking about the project, let's get into a bit more detail about how that project is working exactly. So HIPSO-1 is just part of a much bigger oceanography mission that you guys are running at NTNU. Could you give us the big picture on that project and tell us a bit more about how it came to happen?
Yeah, oceanography has been a focus for different research groups at NTNU for a very long time, and there has been a lot of effort on building different sensor agents, autonomous sensor agents, such as drones and surface vessels, and also subsurface vessels. Some years ago, also the idea to bring the satellite into the picture was formed, and of course we can benefit by using Earth observation data from, for example, the Sentinels also. But what we want to do is to make our own satellites that can do more detailed images in locations where we can direct them to. So we want to try to get all these different sensors from the satellite down to the surface or subsurface vehicles integrated into one larger system of systems, so we can get them better information about the environment in specific locations. So I think that's the forward plan and the big idea behind it.
Yeah, and a really fascinating and super important idea. From the big idea, maybe we can go down to some of the nitty gritty. Could you talk us through the actual payload that's going to be on this satellite? What are the technical capabilities? And also it'd be really interesting to hear what parts of it your team has developed in-house.
Yeah, maybe we can start with the last part of the question first.
Sure.
We made the processing unit and software and built a camera system based on COTS optical components that we adapted for space. So we built more or less the full integrated camera and the processing unit. It's based on that, also is based on commercial available electronics, but it has been adapted to space.
Okay, and what about the area of coverage, for example? Once it's making a pass, could you talk us through how big an area it's going to be able to cover in terms of observation?
Standard configuration that we're planning to use on the satellite, we will cover about 50 by 50 kilometers with a fairly high spatial resolution and a spectral resolution of lower than 5 nanometers in the 400 to 800 nanometer range. So that will make a hyperspectral image cube called a cube, as in 2 dimensions you'll have the spatial information like a regular image, and then the third dimension you'll have the extra color information or spectral data.
Okay, fantastic. What impact are you hoping to achieve with HIPSO-1 in terms of our attitude towards ocean health? And do you think in general that global efforts are growing to monitor the ocean from space?
What I would like to say about that is our satellite will be capturing relatively small areas compared to the Sentinel program, which has a much more global scope. But the type of data that we're collecting, namely the hyperspectral data, is quite unique in a ocean color or ocean perspective. So hopefully the data that we are collecting combined with the extra autonomous agents and platforms that we will be deploying at the same time and locations will help gain more insight into how we can utilize hyperspectral data, as well as what kind of insight this type of information can give for the insight to how ocean and ocean systems work And yes, I think this is very important. The ocean is quite big and quite important for all life on Earth.
Yeah, it certainly is. Anything, Roger, that you would add to that in terms of the outcomes that you're hoping to achieve from this mission?
I think it ties back to what I mentioned earlier, that we really want to see this chain of data from different sensors and be able to do more kind of directed missions where you can pinpoint the locations, you can pinpoint the type of data that you want that is important either for your research or for investigating special phenomenon that might happen. So I think the important part is that we can, even though we can't take a lot of data covering the whole Earth in a day, we can be agile and flexible, and we can use the satellite to kind of go where we want to and get the data from the areas that are important.
Fascinating. Well, as I said, a really interesting project and a really, really important mission, as you guys were both saying as well, in terms of maintaining the ocean's health. Sivert, Roger, thank you so much for taking the time to talk to us today, and really, really hope that the mission deploys correctly and that you can continue this really important work that you've started. I'd also like to say a big thank you to all of the guests who've taken part in our Q&A today. It's been fascinating to talk with you all, and we're about ready to switch back to SpaceX's live stream to see the satellite deployment. So it's fingers crossed time, and after that we'll return with a final word from the studio after what will hopefully be a successful deployment.
Welcome back to the Transporter-3 mission, our third dedicated rideshare mission. Falcon 9 lifted off at 10:25 a.m. Eastern from Cape Canaveral Space Force Station, had a successful stage separation, landed first stage back at landing zone 1, and successfully completed our first second stage burn. We're now waiting to relight the MVAC engine on the second stage for the second and final burn. Welcome back to the Transporter-3 mission, our third dedicated rideshare. And we're anticipating that to begin in just a couple seconds.
MVAC ignition and shutdown.
All right, as we saw there on your screen, like I mentioned, only a 2-second burn, super quick.
Nominal orbit insertion.
Okay, and there we heard the call out that we have confirmation of good orbit. Next up, starting around T+1 hour, we will start the deployment of our 105 spacecraft. As I mentioned earlier, this is our third dedicated rideshare mission. Our goal with these rideshare flights is to provide small satellite operators with competitive pricing, increased flight opportunities, and flexibility. These dedicated rideshare flights to sun-synchronous orbit will occur about 3 times a year, providing regular access to orbit. Additionally, we offer opportunities for a ride to orbit on our Starlink missions, which launch every couple weeks or so. Coming up in approximately 2 minutes, we're expecting the start of the deployment sequence. There will be 82 deployments for 105 spacecraft, which will occur over a 30-minute period of time. These deployments include microsats, CubeSats, pocket cubes, and orbital transfer vehicles, which are sometimes called space tugs. And they will deploy the spacecraft after separating from Falcon 9. Many of these deployments will be grouped within seconds of each other. As I mentioned at the start of the webcast, due to the lack of ground station coverage at times and the position of our camera, we expect only a handful of our deployments to be visible today. However, we do expect to have telemetry and hear audio confirmation over the nets when in range of the ground stations. So you should hear a call out from our mission operators as each deployment happens. And keep in mind, most of these deployments include multiple satellites. So while there are 82 individual deployments, at the end...
Acquisition of signal, Bangalore.
At the end, we will have put 105 satellites into orbit. It's also worth mentioning that because many of the spacecraft are being deployed in groups, and because there is a large communications blackout during the deploy sequence, we won't be able to confirm every deployment in real time. You should hear most of the deployments called out by the operator on console, but for any reason that we don't hear in real time, we will try to provide updates by the close of the webcast. So we're about to start our first batch of deployments. Over the next 8 minutes, we are expecting to hear the callouts for the 26 deployments and have a handful of live views. Several of the customers on board this transporter mission have multi-launch agreements with SpaceX, so some of the names might sound familiar to those of you who have tuned in for previous rideshare missions. To see the full list of deployments, head over to SpaceX.com. We're expecting our first deployment in about 10 seconds. As I mentioned, this is a batch. So let's listen in for this first batch of deployments.
Unicorn 2E separation confirmed. Alpha 2 separations confirmed. Pod-3, separations confirmed. ETVA-1, separation confirmed. EPSO-1, separation confirmed. Gossamer Piccolomini, separation confirmed. DEWA-SAT-1, separation confirmed. NUX-1, separation confirmed.
Welcome back to the Nano Avionics live feed of the SpaceX Transporter-3 mission. And fantastic, we've had a successful deployment of the 3 satellite missions that were on board the Falcon 9 today. So congratulations to everyone. And Rolanda, can you tell us a little bit more about what happens next? These small objects, tiny objects, are shooting around space at phenomenal speeds. How are we going to pick them up and what's going to happen next?
Yeah, so once the satellites are deployed, most of their subsystems are turned off. Only the UHF receiver works. After some time, UHF antennas are deployed automatically, and in case there are deployable solar panels, they are also deployed automatically. Once UHF antennas are deployed, they have basically omnidirectional antenna pattern, so which means that it is quite easy for us to catch the signal with the satellite because no big pointing accuracy is needed to do that. And then comes the fun part, and it is, I think, the most exciting moment for whole company workers, and even if satellite flies over our ground station at night, we still would be there and wait for the first signals. From the pre-calculated TLEs, we know preliminarily when the satellite is going to fly over our ground station, and by the first contact we turn on UHF transmitter, and the UHF transceiver is then fully on, and we can communicate with the satellite. After that, we turn on the S-band transceiver, so we could fully communicate with the satellite and gather telemetry in bigger amounts, because S-band has bigger data rates. So also then we turn on other subsystems, check satellite's health, and then start commissioning.
Fantastic. What an amazing process, and lots of exciting things yet to happen. So I wish you very good luck, and I can tell that you must be really excited, having personally worked on one of these missions yourself. Rolanda, thank you so much for all of your support today and all of your technical know-how. You've given us some brilliant insights into the manufacturer side of how this process works. Let's hear a little bit from our customers and stakeholders for the missions on board and get their reaction to the successful deployment of these satellites. So over to you, Charles. We've seen the successful deployment of your satellite. Sum up how you're feeling right now.
Ecstatic, absolutely delighted. It's been a long journey. for me, and of course for all the team. We've got an amazing team here at CEN, and we've had an amazing journey also with the Nano Avionics team. So absolutely brilliant to finally reach this fantastic milestone, and really puts us in a good position now to develop the company rapidly and to deliver our vision of democratizing space using video. So thank you to everyone within the CEN team and to everyone at Nano Avionics for all your hard work and skillful work to get us to this stage. So really excited to the satellite.
Brilliant. Thank you very much, and congratulations to you and everyone at CEN. And Roger Sivert, you've just seen your satellite and all that incredible technology that you've been developing float off into the cosmos. How do you feel having seen that successful deployment?
This is very cool. Now it's just to sit back and wait for the first contact. That will be a very exciting moment.
Yeah, very exciting times ahead, certainly.
Fantastic. Well, that just leaves me to say a huge thank you, first of all, to all the guests who've joined us either live in the studio or remotely, and to all of the viewers, all of you guys at home, for joining us for this live stream. Please do follow us at Nano Avionics on our social media channels so you can stay updated on the development of other satellites and those upcoming launches, and also see the progress of the ETV A1, DEWA-SAT 1 and HIPSO 1 satellites, as well as other upcoming launches. Thank you very much for joining us, and goodbye.